Okay, so this is part of a school assignment. My group that I'm working with has to solve one problem and post it on a discussion board. And our problem is 1.49. I'm not sure if videos are okay, but I just feel I can convey, I guess, what I'm trying to say better this way than I can if I just write it out a block of text. I think it helps me learn better. I think it'll help students learn better and maybe even other people as well. Okay, so that's what I'm going to try to do, and if I'm not allowed to do that, then there obviously won't be any more videos for this type of stuff, but we'll see. We'll see how it goes. So this is the integral we have to evaluate. We need to do it two different ways. And we'll do the easiest way first. So the way that we're going to do this for this particular problem is we're going to work with our divergence here, okay? So the divergence, this part, we can get by using the divergence theorem, which is our integral of this is equal to the integral of, so I guess I'll go ahead and write it out like what we have. So this will be equal to the surface integral of r 1 over r squared r hat dotted with sine theta d theta d phi, which we've done in class. We know that this is going to give us 4 pi if we go ahead and finish that integration. Sine theta d phi, that'll give us our 4 pi. So that's where that comes from. And okay, so we know that now. So now we can say that our j is the integral v e to the minus r, and then I'm going to multiply by 4 pi, that's our divergence. And we're going to use our delta function, which is three-dimensional, x, y, z, d tau. The 4 pi is a constant, so I can factor that out. And we can use our property of the delta function here, which is, for our delta function, it picks out basically the one point where our function is, it blows up, it spikes up, right? That's the whole point of our delta function. That's the unique aspect of it, which will be at 0.0, which means that that integral is really just 1, if you just integrated our delta function there. So, okay, 4 pi e to the 0 is just 1, so we get just 4 pi. Okay, so that's using our delta function, that's using divergence theorem. Cool. That's the easiest way to do it, I think. And there's a second way as well, which we'll work through here. And that's using our integration by parts equation, which I highlighted 1.59. I'm going to just rewrite it out down here. So we have the integral. I don't know who that is. I'll talk to them later. Sorry. Of the divergence of FA. Number's been calling me a lot. Maybe that's important. D tau is equal to the integral F, the divergence of A, d tau, plus the integral of A dot grad F d tau. Okay. And that's equal to the closed surface integral of, it's an awful circle, Fa dot A. And just rewriting it here. The integral over volume of F divergence of A d tau is, if I move that over, I'll have my negative. All right, so just moving this guy over. A dot grad f d tau plus, we're still going to have our closed surface integral, fa dot dA. Okay. Now we can kind of see what we have here and compare this to what we have, right? Well, E is kind of like our F, right? And A is kind of like our R hat over R squared, right? So it's the same idea. It's set up that way. So I'm just going to plug in what we have, what we know, into our F and our A. And we get negative the integral over some volume, R hat over R squared. And then we're going to dot that with the gradient of e to the minus r d tau. And then we have our closed surface integral here, e to the minus r hat over r squared times dA. And this is just minus e to the minus r hat. Okay? So I can put that in here, and what we end up getting is our volume integral minus e to the minus r over r squared. And then let's not forget what d tau is. D tau is our volume, right? So I'm going to multiply that by r squared sine theta d theta d phi dr. So that's our volume element, d tau. This is the r squared part. That's our volume element. Okay, cool. I'm going to go ahead and just do this part first. Okay, so we kind of already know what sine theta d phi gets us. That's going to be 4 pi. I'm going to factor out this negative, and we're left with just the integral from 0 to r, e to the minus r, which is 4 pi e to the minus r. Now that's positive because the negative and the negative go away. I made a mistake there, so be careful. From 0 to r. Another place I made the mistake is I forgot to evaluate at 0. So you get 4 pi e to the minus r minus 4 pi, because e to the 0 is just 1. Okay? So that is one part. Okay, so we have that. Our dA, our area element, we know what that is. That's r squared sine theta. We've calculated that before. D theta, d phi, r hat. So then if we calculate this surface integral, that's the other part of that's this part. We just calculated the volume integral. I'm just breaking it up into two integrals here. Is the integral, make that a little nicer, e to the minus r times our area function, so sine theta d phi. And that one's pretty straightforward. We're going to just get this is essentially a constant. It doesn't depend on theta or phi. So we can factor that out and just integrate this, which we've done a million times at this point. That's just 4 pi e to the minus r. Now to get the total, we have to add this part with this part, right? Also, there's a negative out here. I forgot. So look at me making a mistake. So that negative is going to change the sign. So let me fix that over here. This becomes a plus. This becomes a minus. That's good because we have to add these together. So this part over here, that's coming from this, our surface integral. So let's add them. Minus 4 pi e to the minus r, right? So that's one part. plus 4 pi. Let me actually double check this. Did I factor that negative out and that's where that went? So this should be actually a minus and a plus. And now when let me fix this. Now when we do this, we can see that the total we get is in fact 4 pi, which agrees with what we got earlier. So those were two ways that you could go about solving this integral. And they both give you 4 pi there. So hopefully that does what it needs to.